Today we are going to discuss electric field inside an uniformly charged solid sphere that has radius r. Here I have not drawn the solid sphere properly, but try to imagine it as a sphere, solid sphere. Here it is a radius r, and it is uniformly charged solid sphere which has charge q inside. Now what is our aim and what is the question? So it is an uniformly charged solid sphere which has radius r and inside enclosed charge is plus q. So our question is, outside the solid sphere, what will be the electric field? So outside the radius r solid sphere, what will be the electric field? So now let's calculate. So first of all, I will now erase these things. So here, you know what formula will be applicable? Here we have discussed about the formula named Gauss's Law. We have discussed about the formula Gauss's Law in my previous lecture. So here we will apply Gauss's Law. So what is Gauss's Law? Let's write that. Gauss's Law is actually closed loop integration E dot ds vector, E dot product of ds vector equals q enclosed by epsilon naught. So this is actually the Gauss's law. That means what is E dot ds integration? Integration of E dot ds, it is actually the flux through any closed surface, that is equals to enclosed charge divided by epsilon naught. Epsilon naught is the permittivity in the vacuum permittivity. So first of all, we have to remember that we will apply Gauss's law here. So step 1 is, so for applying Gauss's law, what we have to remember? We have to remember, for applying Gauss's law, we have to consider a Gaussian surface. We have to consider a Gaussian surface. So let's consider a Gaussian surface. Where we have to obtain the electric field, that is outside the sphere. So let us consider a Gaussian surface that will be, let us consider this is a Gaussian surface and it has radius, let us consider small r. Small r is the radius of this Gaussian surface. Let us name it as Gaussian surface. So now how we will calculate this Gaussian surface? Let me draw clearly this Gaussian boundary. It is a Gaussian surface of radius r. So we will apply the Gauss's law formula. What is the Gauss's law formula? Let's return back to that. First erase it. So Gauss's law formula was that I have written just previous, that E dot ds integration, closed loop integration E dot ds, that is actually flux, electric flux, equals q enclosed by epsilon naught. So writing the Gauss's law here, what is the formula? Closed loop integration, formula will be closed loop integration. Let us write me the formula. Integration, closed loop integration E dot ds vector, that is area vector, is actually area vector, okay, that is equal to q enclosed by epsilon naught. So when we have drawn the radius r uniformly charged solid sphere and the Gauss's law of radius smaller, here I have drawn in the previous that it is the Gauss's law of radius smaller. So for smaller, what will be the radius for radius, what will be the area? Area will be 4 pi r square, because we all know this is the area of any spherical element. So erasing it, because we have considered a Gaussian surface, we have imagined a Gaussian surface that is radius of small r, and the sphere has the radius capital R. So for the radius of smaller radius, what will be the area element? Area element will be, let me take the pen, area element will be, let us consider E dot 4 pi r square, small r square, and what is the enclosed charge? That is small q by epsilon naught. So we got it. So what we got, that mod E dot 4 pi r square, and that is actually radial vector. So cos 0, theta is 0 there, because we know for dot product E dot ds cos theta, so theta is 0 there because electric field is acting radially. So for theta 0, cos 0 equals 1. So writing again clearly. So what we have done here, we have done, firstly we have considered that Gaussian surface that has small radius smaller, and that has area element or area 4 pi r square. Now we have dot product of electric field with that Gaussian surface area, that is 4 pi r square. So E dot ds cos 0, and cos 0 is what? Cos 0 is 1. So I am writing here only the magnitude here. I am not directing the direction. First, before writing magnitude, E dot 4 I r square. This dot is not dot product now because we have done dot product already, that is cos 0. So E dot 4 pi r square, that is equals q by epsilon naught. So magnitude of the electric field outside an uniformly charged solid sphere will be q by 4 pi r square epsilon naught. This is the magnitude of the electric field outside the uniformly charged solid sphere. Now you will tell me that it is electric field, na? It is electric field. Electric field is what quantity? Electric field is what quantity? Electric field is vector quantity. And what we know by the definition of vector? A vector is a physical quantity that has both magnitude and direction both. So we have got here only what? We have got here only the magnitude of the electric field. So direction of the electric field will be what? So direction of the electric field will be, so writing the vector form of electric field, we have not taken the mod here. For mod means magnitude. First write the magnitude, q by 4 pi epsilon naught r square, and that was radially acting electric field. So for radial component r hat. So it is the Gauss's law for uniformly charged outside an uniformly charged solid sphere. Thank you.